was born in New York City, actually Brooklyn. My parents got married here. They were both immigrants. My father came from what was then Russia, what later became Poland. My mother came from what was then Austria. So I said they met and got married here. So I went to public schools, mostly around New York City, in various parts of New York City. Then I went to a rather good high school. It was called Townsend Harris. It's now defunct, and people are trying to revive it unsuccessfully. But it was affiliated with City College. And Townsend Harris was a pretty high-class high school. We had for the most part, very good teachers. As a matter of fact, the chap that taught me French was a chap named Mario Pei, who became a professor of languages at Columbia University and was one of the 2 or 3 leading linguists in the world. He was my teacher during the Depression days before he had gotten a PhD at Columbia. So these are my recollections of Townsend Harris High School. Well, it turns out that they didn't teach chemistry in high school there, but they did teach physics. And there were 2 teachers who taught physics, and both of them were sort of eccentric and not very good. But very fortunately, I had a couple of student teachers. And these student teachers were full of beans and very enthusiastic. Well, I found physics to be a real eye-opener. Great course. I just laughed that stuff up. I like mathematics, but physics was just great stuff. It's interesting, at that time, there were a couple of things they explained to us that I didn't quite believe. So I thought about that. But anyway, I went from Townsend Harris High School right into City College. That was in 1933. I wasn't quite 15 years old. And in those days, there wasn't any trauma about which college you were going to go to. I had a very simple choice. It was either City College or it was nothing. And at that time, tuition was free, and we could afford every bit of it. This is sort of during the Depression. I did have something they used to call a Regents Scholarship in New York, which paid $100 a year for 4 years, and that's what paid lab fees and a lot of other incidentals, so I was able to supplement my income a little bit. And in the summers, I would go off to the Catskills and work as a busboy or wait in the Borscht Circuit. That's where you supplement our income. But anyway, when I got to City College, it turns out that I couldn't take physics the first year because it was closed out, and so I took the introductory course in chemistry, and I thought that's pretty nice stuff too. So then I didn't know quite whether I was going to major in chemistry or in physics because they were both eye-openers, and the reason that I picked on chemistry was because I'd never heard of a physicist getting a job, which is rather interesting. Later on, I found my instructor in physics at City College. My second instructor in freshman physics was a chap named Walter Zinn, who I found out later, who got his PhD with a chap named Fermi at Columbia. The name Fermi didn't mean anything to me. Walter Zinn later on turned out to head up the Argonne National Laboratory. So this is the kind of ferment that was going on at the time that I was sort of out of. So anyway, I ended up majoring in chemistry, and since of course it was a toss up between physics and chemistry, you might suppose that I was interested in physical chemistry. And finally, as a senior, I ended up in physical chemistry at City College. And in those days, at City College, physical chemistry attracts either the best teachers or the worst. And at City College, they were among the worst. There was an old chap who was practically senile, and there were a couple of young chaps that were lousy teachers and sadistic graders. So I listened to this lecture in physical chemistry, and as I say, my first impression of him was that he was a clod. And years later, when I became as old as he was and as experienced as he was, I thought he was a bigger clod. But the way I learned physical chemistry as an undergraduate, there was a very fine book called Getman and Daniels, and I proceeded to ignore the professor and study it right out of the book, and I found that was a joy. So there were certain things about physical chemistry that were eye-openers. For example, in qualitative analysis. There was such a thing as an Ernst equation, and it was always fascinating to me how come a galvanic potential would have an equation that would contain a gas constant in it. And later on, when I was in physical chemistry, then I learned it. So actually, they didn't teach a second semester of physical chemistry at City College at the time, but later on, when I was studying for a civil service examination, I went and I just got myself the textbook and worked through the second semester of physical chemistry on my own. Okay, well, I ended up with, I also was interested in teaching, and in those days, one's ambition was to get a job teaching in high school, and so I took a number of education courses, which in a way handicapped me a little bit because I really should have had more mathematics, and this was quite a good school of education, quite a good department of education, but I must say that of the courses I took, most were a waste of time. I think most everything I learned could have been given in one course, but I ended up doing some practice teaching, and that was an interesting experience, particularly since I was no older than most of my students. Again, what happened to me was, after I got my degree, I was taking civil service examinations, and I ended up getting a job as they call a minor laboratory apprentice in Food and Drug Administration in Washington. And I ended up taking care of a bunch of laboratory animals in the pharmacology division of Food and Drug Administration, and I was paid the princely sum of about $1,020 a year, which even back then wasn't much, but I found room and board came fairly inexpensive. In fact, I was sending a little money home out of that.
And what year was this?
Oh, this was 1930. Well, that was 1937. I worked at various jobs in the food and drug, and finally I ended up getting a job as a junior chemist in color certification section. Well, in the meantime, I was going to school in the evenings, and the credits were coming on very, very slowly. And I was working, there was nobody in physical chemistry at the time worth working with that I could get to, and I was working with an organic chemist. I ended up making a physical chemistry problem out of my master's thesis. It turns out, incidentally, that my professor didn't understand what I was doing. He had postulated there were some oxonium compounds in a particular cleavage reaction of diethers, and I proceeded to freeze the oxonium compound out and give it to him. And he didn't realize that something like a 50-degree melting point maximum meant something in the phase rule, and he ended up, I ended up not getting a master's degree there because, by good fortune, I had been looking around I wanted to get back and get a PhD. It turned out that my professor, of blessed memory, knew a Professor Paul Gross at Duke University, and I wrote to Professor Gross, and he said, yes, we happen to have a teaching assistantship available. It was a sponsored assistantship, and on 2 weeks' notice, I quit my job, sold my car, and went down to Duke University. Well, that was kind of an eye-opener because, it was nice to watch the credits pile up, and although I had been now a number of years out of, I had been going to evening school, but I began taking some real physics courses, like theoretical physics and quantum chemistry. Incidentally, Fritz London was there teaching quantum chemistry. So I ended up getting a degree in physical chemistry, and as I said, I shared a laboratory with Harold Shiraga, and we used to help each other out. I called him research director, he called me research director, and I think we helped each other out more than our research directors did, because we were working in a problem that neither of our directors was really that familiar with. And besides, they were busy with other things. There was a war going on. In 1947, I ended up with a PhD. And in the meantime, I was looking for some jobs. I turned down one academic job in Utah because we figured we would never be able to get back home. And I ended up getting a job in the Bureau of Mines, and I had a friend in Pittsburgh who worked at the Bureau of Mines, and I think that contact helped. So I began getting a job at the Bureau of Mines, and I was working in Fischer-Tropsch reaction. And I was working with Lawrence Hofer and Saul Weller. Saul Weller was a neighbor and a colleague, and Larry Hofer was my immediate superior. Incidentally, he's still in Pittsburgh, and we're still good friends. It's interesting about that time, we were moving our laboratories from Pittsburgh to Brewston, which is a suburb, and we couldn't do experimental work because the electricity wasn't in. And
now, what year was this?
This was now about 1950. I was 47. Around 1949, really. And Larry Hofer told me one time that when he was taking physical chemistry, what used to bother him was that they used to derive the equilibrium constant by assuming the Goldberg-Wager mass action law in both directions, and then the quotient would give them the equilibrium constant. But then when you would go to the chapter on kinetics, you were told that you didn't know the kinetics of the forward or the reverse reaction from basic principles. So the question is, what did this do to the derivation from the Goldberg-Wager, which we knew wasn't accurate, but the next question was, why did it always give you the right answer? And I was talking about this to Saul Weller, and he gave me a paper by Gatsby, Hinchey, Whitney, Sykes. And I worked up a paper on relations between forward and reverse reaction rates. One time, we had sent this into the journal, and I was giving a staff talk on it. And while I was preparing the staff talk, I got to the point where I was interested in the relations between the forward and reverse reaction rate, and I said, my God, this doesn't work. And I fussed about that all day, and I finally convinced myself that there was no such relationship. And the reason there was no such relationship was there's no unique way of writing an equilibrium constant. The fact remains, for example, from the thermodynamic point of view, you can take X moles and then you multiply the constant by a factor, or you raise the constant to an equilibrium, to an exponent of X. And of course, what that does to your and your thermodynamics, it doesn't bother at all, but that louses up your kinetics. So we ended up thinking about that, and this was about the same time Moriuti was coming up with the stoichiometric number. And we sent this into the Journal of Chemical Physics, and they accepted this. And so this was some usefulness that we got out of, this was a useful result we got while we were waiting for something to happen. And Larry Hope was the one that sparked it, and I kind of put it together. So we published a paper. That was the Manes-Hofer-Weller paper, which has stood up pretty well over the years. But then, in the meantime, we were doing some catalysis work, and we found out we wrote a paper on finding out something about the structure of carbides in Fischer-Tropsch catalyst. Incidentally, at the time, I was doing some work on the hydrogenation of carbon monoxide to methane on a cobalt catalyst. And I found that the less carbon monoxide was in there, the faster it went. It was just sort of an inverse order in carbon monoxide. And in fact, I never could pump it fast enough over the catalyst, no matter how small amount of catalyst I took. We never did anything with that. Of course, later on I found out that the cobalt catalyst was the ideal way of getting carbon monoxide out of synthesis gas, out of an ammonia synthesis gas. So this comes to the head of what we didn't notice. Well, I thought I would try my hand in private industry, and I ended up working at Koppers in their fuels processing division. Then I got into statistics. The research director thought it would be a good idea to have somebody learn some statistics, and I did.
Who was the research director?
A fellow named Paul Bachman. Apparently, he had come from Grace, and he had reconverted a chemist to a statistician, and thought it was a pretty good idea. But when I went around and took some courses, I began to realize that the equivalent of a PhD in chemistry is a PhD in statistics. And I realized that as time was going on, I was going to be a half-baked statistician and no longer a chemist. And besides, I said to myself, even if somebody offered me a PhD in statistics, would I want one? The answer is no. And it turned out that there were some chemists who had made pretty good statisticians, but generally these were people that hadn't really amounted to much in chemistry, and really they had found a new métier, and so statistics was okay for them, but not for me. So I ended up at Pittsburgh Coke and Chemical Company, becoming a physical chemist again. In the meantime, incidentally, I did this on my own time. I've gotten interested in this work on reaction rates close to equilibrium had gotten me interested in relations between acoustics and kinetics, and also I had gotten interested in non-equilibrium thermodynamics. And I came to the conclusion that much of non-equilibrium thermodynamics was the radar echo of one's own mathematics. In fact, Prigogine, for example, later on got a Nobel Prize, incidentally, had made a big deal of what he called, he had called this thermodynamic coupling, in which he would find, in which he postulated that some reactions would be going in an anti-Gibbsian direction if enough reactions were going on, and it turned out this was the radar echo of one's own mathematics, and a chap named Koenig, very fine thermodynamics, had shown that if you simply redefine your chemical reactions, you could turn this thermodynamic coupling on and off. And then someone says, well, you can't do that. And I was able to show that you could turn thermodynamic coupling on and off by infinitesimal perturbations from equilibrium, and shown that it had little or no physical content. And then we were able to show that many of these so-called symmetric phenomenological coefficients could very easily be explained in terms of very familiar thermodynamic and kinetic quantities. I wrote a paper on this, and it turns out I had a tremendous amount of referee flack on this, and I ended up having to break the paper into three parts, so that each part would have to get through a referee separately, and there would be nothing to argue about. For example, the first thing I did was to write the paper on thermodynamic coupling. Actually, what had happened is one of the reviewers sent me a copy, a reprint, probably to show me what the real truth was, and I found out that paper had a hole in it wide enough to drive a truck through. And so we ended up publishing a paper, in fact, and that was the paper showing that the thermodynamic coupling is the radar echo of one's own mathematics. And then it had turned out that, and this is in the Rhodes book on non-equilibrium thermodynamics, it turns out that if you took this so-called matrix of phenomenological coefficients and diagonalized it, according to the Rhodes, you got nothing physically interesting. Well, I went and taught myself some matrix algebra, and it turns out that there are two ways of diagonalizing a matrix, and they had picked the wrong way. And we were able to show that, in fact, if you knew, you could explain what the diagonal matrix was very simply, and what the cross coefficients were again very simply, and we straightened that out. And finally, I was able to publish a paper on explaining on a thermodynamic and kinetic basis such things as the thermocouple and the thermocell, and call this again, and streaming potential. And that one was published in the Journal of Physical Chemistry, and I wish I knew who the reviewer was, because this reviewer was a sharp cookie who knew about thermodynamics and physical chemistry, and he got the message, or she. But there are times when you'd be very satisfied to get a good reviewer. But this was done on my own time pretty well, because nobody was paying me. What happened was that at that time we were members of a babysitting cooperative, and what I would do is I would take on the babysitting chore. When it was my turn, it would be at nighttime, and I would pick on young kids who would go right to bed, and then I would stay up and do my work on my non-equilibrium thermodynamics. I was asked, Howard Schirag had asked me to write a monograph on the applications of non-equilibrium thermodynamics to problems in biology, and at the time, when I looked into it, I came to the conclusion that the reason why the biologists were giving it so much attention was because they were more easily snowed by the mathematics, and that really not much was going to come out of it. And that's turned out to be the case. You don't hear any more about non-equilibrium thermodynamics in biology. It turned out to be an excellent way of making simple concepts difficult. So I had really said everything I was going to say about that. It's interesting, incidentally, in some of the early work which I had done, I got into, again, relations between kinetics and acoustic absorption. This is the stuff, of course, that later on Manfred Eigen really picked up on. I remember mentioning to the boss at Burt Davis, a very good physical chemist, that there really should be absorption of sound in a chemically reactive medium, and he was very skeptical about the whole thing. But it turns out I was running through the literature, looking for another problem, and I ran into a paper in the Chemical Abstracts which said, absorption of sound in chemically reactive media. You know who wrote that paper? Albert Einstein. And he had worked out the 2NO to NO2 equilibrium, and except for one minor typographical error, had really had worked out a good bit of the mathematics. It turns out there's a book which says that Manfred Eigen was the first to be into fast reaction kinetics, and I think first is not right. Einstein is first. I would say Manfred Eigen would be foremost, which is perfectly all right. But anyway, that was some contacts I had. In the meantime, when I got to Pittsburgh Coke and Chemical, I was working on such things as a catalytic melamine synthesis that they were interested in for a while. I got into the thermodynamics of blast furnace operation. Wrote a paper in the Journal of Metals on the thermodynamics of blast furnaces, which turned out to be quite a fascinating business. And in fact, we calculated on a theoretical basis what the coke use should be, and we calculated, for example, whether fuel injection would be an efficient way of reducing the amount of coke used in the blast furnace. And that turned out to be reasonably well. The blast furnace was really fascinating in a way. It turns out, for example, when I read a book by a chap named Johnson written about the First World War, and he found that in wintertime, blast furnaces worked better. And he found out that that was because the air was drier. And so they found out that when they dried the air into a blast furnace, it would be more efficient. Then in recent years, the Russians had found that when they added water to the blast air, it would be efficient. It would be more efficient. Turns out they were both right. What had happened was that over the years, the preheat temperature in the blast furnace had gone higher and higher. And what happened is that changed what the engineers called the pinch. It used to be that the furnace was pinched by having enough heat available to fuse the iron. And then what happened is the pinch turned out to be the endothermic reduction of FeO by carbon. And it turned out there that there was enough heat to go around, and the hydrogen you generated from the water was in your favor. So we worked out all of those little details, and I ended up getting a small bonus. But but there were the two most interesting things I did at the Pittsburgh Coke and Chemical. One was we picked up on the paper by Koch, Tobin, and Emmett. This is the microcatalytic reactor, which was pretty well invented in the Gulf Fellowship in Hall's group. And what we did was we decided that what we would do is to see whether we could study the phthalic anhydride synthesis using a microreactor, where we used a catalytic reactor of about less than 1 cc. We found out that the microreactor was more accurate than the pilot plant reactor, because the pilot plant reactor, you had trouble, you didn't know what your temperature was. We developed that for almost a couple of years. A chap named Dick Grant really carried the ball on that, and we got to the point where we could really do a complete analysis of all of the products from the phthalic anhydride synthesis, and we were able to close a hydrogen, a carbon, and an oxygen balance. And in fact, we were able to calculate the rate of heat production, and we ended up with a set of data that the engineers could use to design a plant, and unfortunately, we couldn't publish any of that. But in the meantime, I was also working for the Carbon Division, again with Grant, and I succeeded a chap named Stanton B. Smith, who is, I guess, still active as a consultant in the carbon business. And he had gotten started on applying the Polanyi model to adsorption, and that got me into the Polanyi model. So we sort of picked up on the Polanyi model and ran with it. And originally, originally there was one group that was working on gas phase adsorption and another group working on liquid phase adsorption. And what I was able to do is put the two together and relate liquid phase to gas phase adsorption. About this time, there was another reorganization, and as a result of this reorganization, I ended up at Mellon Institute, and that turned out to be a good springboard to go to Kent State University, to get myself an academic appointment, and I ended up getting an appointment as a professor at Kent State University, and it turned out there that we had done research in a number of fields, but mostly we continued our work in adsorption. And later on, we did get some support from the National Science Foundation and from the environment, from the Environmental Protection Agency. But in the beginning, we did get a good bit of research support from Calgon, and we were able, for example, to work out computer programs for them whereby they could do multi-component adsorption in a column. So it turned out that the support they gave us was a good deal for us and a good deal for them. And that was rather mutually satisfactory. And so we ended up publishing a series of papers in adsorption where we did, if we include the work at Pittsburgh Carbon Company, or Pittsburgh Activated Carbon Company, and so forth, at Mellon Institute. We ended up doing some work on single component vapor phase adsorption, multiple component vapor phase adsorption, single component liquid phase adsorption, multiple component liquid phase adsorption. Then, when I got to Kent, we did adsorption of organics from water, and then we ended up doing multiple organics from water. Then we ended up doing the effect of pH on adsorption. And mostly what we did was milked old Polanyi. And we found out that we had a good basic model. We made some changes. The changes were mostly fairly straightforward. At a time when Calgon was busily putting all of our results to use, a number of other people were doing a good job of systematically ignoring it, which was all right with us because we were able to get our work done. This kept us going. And I retired from Kent State University in June of 1985, and I've been here in Pittsburgh ever since. Back to Pittsburgh, where I got my first post-PhD job. Of the papers I'm most happy with, there is the one with, there's the Manes-Weller paper. I think the early papers on relation between acoustics and kinetics I'm pretty happy about. The work on non-equilibrium thermodynamics, I think there were a couple of good papers there. I didn't do anything in the field because what really happened was I published everything I had to say, and there really wasn't anything else I could do. That work was picked up, incidentally, by a chap named Drexler, who was interested. He's a doctor who was interested in cell membrane processes, and I think he ended up showing that you could get membrane processes that did not even follow the Onsager reciprocal relationships. And I would say that field was pretty well sort of washed up. The work on physical adsorption, I think some of that still could be continued, but the last paper I did on my grant was using actually applications of the Polanyi model, qualitative applications to extract traces of refractory materials from activated carbon. What happens is that if you put material on activated carbon is very difficult to extract, like, say, anthracene or benzanthracene, and you now put on, say, 0 milligram per gram or something like that, it turns out that the stuff disappears. You just can't extract it at all. And it turns out the reason you can't extract it is because it has a sharply concave isotherm, concave downward isotherm. But we had shown that if you, and it also follows the Polanyi model, that if you have one dominant adsorbate on the carbon and a number of trace adsorbates in addition to the dominant one, if the dominant one is reasonably strongly adsorbed, the adsorption isotherm of all the traces become linear and independent of each other, which means that either you can extract them completely, or if you don't extract them completely, you can calculate what's left on the carbon and thereby do a quantitative analysis. And we got to the point where we could take, say, 25 different materials and displace them with a strongly adsorbed material. This is now published in the Environmental Science and Technology. We used benzanthroquinone, and now you can take something like benzanthracene at a loading of 10 parts per million and pick it up. So this is going to be of some use in stream monitoring, because up to this point, if you had some very refractory material that was on the carbon, you could detect it. And with the exception of a couple of compounds that may react on the carbon, it looks now as though almost everything is recovered. So that's about the last thing we've done. Right now I'm interacting with a couple of graduate students at Pitt, and but I'm not working too hard, and I'm taking piano and enjoying myself. I guess that's what retirement is about.
And when did you decide to take piano?
I had started on piano about 15 years ago, when I decided there just wasn't enough time to do that in our living. I would have liked to have taken it as a child, but I decided that now that I was retired, this is a good way to spend my time. So I got myself a piano and found myself a teacher, and I'm going to work. Keeps me off the streets.
How did you come to go to work at the Bureau of Mines?
Well, I was looking for some jobs, and Bureau of Mines had an opening, and my friend Joe Groomer, who unfortunately spent, there was a chap named Joe Groomer who used to live on the Lower East Side, about 2 blocks from my house, and I first met him in the 7th grade, about 10 years old, and he didn't go to Townsend Harris High School, but he went to City College. We graduated the same year, and we've maintained contact ever since. As a matter of fact, we still have contact with his widow here in Pittsburgh. He's a good friend. And he had gone to Pittsburgh to work at the Bureau of Mines, working with flames and explosives with Lewis and Von Elba and that group. And when I was thinking of taking a job at the Bureau of Mines, Joe Groomer said that Hofer and Weller would be a good bunch to team up with. So I decided, well, that's a good place to go. So that was the contact. And it turns out that Hofer was my immediate superior, and Weller was transferring to coal hydrogenation from Fischer-Tropsch. And what I did is I had to fill the empty spot left by Weller's transfer to coal hydrogenation. They're both very good scientists and good friends.
And what position did Weller have at that time?
Physical chemist.
How would you describe Hofer as a person?
Well, I'm prejudiced. Hofer's a very good friend. But I think in many respects Hofer tends to be underestimated because he doesn't make a lot of noise. But Hofer has written well over 100 papers. He came to work in catalysis. He ended up educating himself in X-ray diffraction and magnetic methods, and got to be very good at both. He was doing all the powder crystallography. Hofer wrote a very fine monograph in which he straightened out the puzzles of the various carbides of iron on Fischer-Tropsch catalysts. And incidentally, right now he's working in for mine safety. Still at the old Bureau of Mines, where building where we originally started. Hofer came on and went to work for Calgon, and in fact succeeded me in heading up the Mellon Fellowship. But then they closed down the Mellon Fellowship. That left him out in the cold. And but he ended up at the Bureau of Mines, and I think he came out smelling like a rose because he's still working and still enjoying himself. Hofer's a very solid scientist, and we've interacted a good deal. Very broadly based on.
Did you have any contact with Storch while you were at the Bureau?
Yes. That's interesting. Yes, I had some contact with Storch. We interacted a bit. As I told you, Storch was the one who was rather skeptical about sound absorption, but of course he hadn't thought about it that much. Storch was happy because one of the things Storch liked was I derived the formula for the total product distribution of Fischer-Tropsch products. Incidentally, that's in the literature. That's called someone calls this the Florey-Schultz distribution. It turns out that what I had done was independently derived the Florey distribution. Florey had done this 2 years before in polymers, but at that time I didn't know any polymer chemistry. But it turned out that in his paper, it turned out that in an ordinary Fischer-Tropsch synthesis, if there was only one parameter, namely the growth probability, then it turns out that if you plotted the diesel oil fraction as a function of growth parameter, it turns out that over a very wide variety of growth parameters, the diesel oil fraction turned out to be very insensitive, and that you never could go above about 28%. And we looked at captured German literature and the like, where they had done everything to increase the diesel oil yield, and they couldn't do it. The last I heard, somebody at Sasol was still trying to do research to increase the diesel oil yield. And apparently, unless you change the mechanism very radically, it's like painting a black cat white. It's a good way to waste your time. But anyway, Storch was a good, solid physical chemist who put together a really good staff. I would say that Bureau of Mines staff was as competent a bunches any I've worked with.
And what enabled him to do that?
You mean how he managed to do that?
Yeah.
I guess he was given a lot of authority and freedom in those days.
But you can pick poor people also if you have
Yes,
given.
but somehow or other he seemed to have a knack. That group has won more than its fair share of Pittsburgh awards. That group had, for example, in it Bob Anderson, Keith Hall, who at that time was a junior chemist, okay, Gus Friedel, Larry Hofer, Saul Weller, Zeke Clark, Benson and Field, who came out with the Benfield process, Irv Wender, who later on got to head up the Bureau, okay? It's sort of fallen on bad days now. Then they did some, Max Lieber did some very fundamental work on fluidized beds. The place was extremely productive in those days. And we made a lot of friends there, who we've kept to this day. It was a good experience.
And what permitted you to have that flexibility to be so productive?
I guess there was an esprit de corps there, and I think that Storch himself was a good physical chemist. I think he was one of Gilbert Lewis's people, and I think in those days maybe jobs weren't that easy to get. It was just opening up, and my guess is those were good jobs, and he was able to pick his people. But how he had the talent for picking all these people, I still don't have to figure it out. But he put together a terrific staff in those days. And I mean, all kinds of members have gotten national awards in that group. You know, you talk about, they talk about government, for example, government of necessity being efficient. Okay? I've never seen that group. I've never worked with that good a group in any private industry that I worked with. It was an unusual, of course it was an unusual group.
And every group like that has some people who are a little different than
Yes?
the average. Were there some in that group that you can recall?
Somewhat?
Some people who, well, we might call characters or...
I wouldn't say that Wenda was a character, but Wenda had a number of... Wenda used to had a staff, I think, where he would be real good at holding their hand and get productivity from them. Incidentally, Milt Orchin was in that group. I think he was one of the inventors of DATCO. See, I'm trying to think about who else was in that group, but I think we really covered it. There was Zeke Clark. There were good engineers, there were good scientists and good engineers, and good pilot plant people. And they really picked up our Fisher Trophy and ran with it.
What do you think caused the atmosphere to change at the Bureau of Mines?
Age, people left, time, less support for synthetic liquid fuels, and I guess nothing lasts forever.
What is your impression of research and industry?
I haven't worked for that many people. It varies. There are people that are very, I'm sure there are some people that are very good, and there are people that, well, the idea of research is to run around in all directions and hope they'll bump into money. But I've seen both. I've only worked for only a couple of places in research. I've met some people who are very good, and I've met some people who are not that good.
But you must not have liked it too well if you left industry to go other places.
Well, I think I always had the academics did have one advantage. In the academics, you have to scramble a little hard. For one place, I guess I always was a frustrated professor in the first place. And the second place, the academics have a freedom to do research, so you can, and there's something nice when you've done a piece of research about not having to get 6 layers of approval before you can send it into a journal. When you come up with something, you send it into a journal, and that's nice. I like interacting with young people, which is kind of fun. I like working with graduate students. I've met a number of people, but I think that it was mostly the idea of freedom to do what you want to do. And as a matter of fact, I think I did Calgon more good as a professor than I would have done for them as an employee, because if I'd been an employee, somebody would have been directing my research.
How do you think industry can incorporate this academic freedom, or do you think they can?
I'm not sure that better ones don't. Because I've known a couple of chemists. Okay, one of my colleagues who just got, one of my colleagues who got out of City College the same time I did was David Breslau. And David Breslau worked for the Hercules Company. And David did an awful lot of patenting and publishing. And he was a pretty high-class chemist. And I would imagine that in that lab, that he probably found that the atmosphere very congenial there. And my guess would be that this would be an example of a high-class jumping research outfit. So I really can't say, in the sense that my sampling of the academic life is probably a more accurate sampling of what goes on generally than my sampling of the industrial. And partly, of course, the friends in industry don't understand what they're doing.
What is the biggest changes you've seen in research since you started and now?
Tremendous developments, of course, in instrumentation. Not having to make your own chemicals, being able to buy whatever you need. But, of course, the expansion of literature. But mostly just this tremendous, this explosive growth in analytical techniques where you don't have to spend too much time wondering about what you've got. Gas chromatography, mass spectrometry, GCMS, all of which we've used. So I would say instrumentation has helped a lot.
And what was the biggest change in teaching over the years that you were teaching?
The overall methods of teaching haven't changed all that much. Of course, the content has changed, of course. I remember one time some administrator was saying that the undergraduate teaching has remained pretty static because he would look at the catalog and he'd find the same course that was being offered 20 years ago. Of course, this person obviously hadn't bothered looking at the textbook. The course may be called General Chemistry now, and General Chemistry 20 years ago, but somebody has kept up with what's been going on. And so this person obviously didn't realize that the titles of the courses remain the same, but in science the content has changed. A lot of that has happened in chemistry. For example, when I first took chemistry, one thought about molecules, but one didn't think of these as objects for which you could determine the size, the shape, and the distances, and the like. So I found myself teaching concepts in chemistry that was not known when I was taking freshman chemistry. So in that respect, the chemistry is kept up reasonably well at times. From some administrators' point of view, what they want to do is give everything a new zonky name, so that it sounds very modern. I don't think one has to be creative about the titles, one just has to include the content. And I think for the most part, the writers of textbooks have kept up. The major disadvantage, as I see it, is that everyone's afraid to throw anything out, and as a result, the books get fatter and fatter and fatter until there's the point that there's more than the student can accumulate. And I think one has to be somewhat careful because one can make the courses so difficult as to take all the fun out. But for the most part, the textbooks that I've seen are good textbooks. Again, the problem is how to get rid of old concepts. For example, from a historical point of view, one can teach atomic weights from the laws of definite and multiple proportions, but it's much easier to talk about, say, molecular weights in terms of what a mass spectrometer measures. So you can say this is a particle, and you don't have to go through a lot of complicated reasoning. I think the Dalton method is interesting, but it's merely historical. In terms of understanding it, it's much really easier to say we we have methods of measuring these sizes and shapes of molecules, and we don't now recognize these molecules. We can use a formula for the molecule, but simply to use a formula for a molecule is to say that an ant might be considered one body and 6 legs. But the 6 legs aren't any old place. The 6 legs are in very definite places. And I think one can talk about molecules the same way. And in fact, it's easier to teach them that way from the point of view of molecular structure and molecular weights. Another concept which dies hard is the concept, say, of normal solutions from the analysis. Unfortunately, there's no calculation you can't do without using molar solutions. The term normal solutions is very confusing because if you take, say, potassium permanganate, which can react in alkaline or an acid solution, if you have a bottle and it's labeled 5 mole of potassium permanganate, you know what's in it. But if you have one that's labeled 5 normal potassium permanganate, you don't have the slightest idea what's in it. So I kind of think that the whole idea of using normal instead of molar is to get away from stoichiometric ratios. But stoichiometric ratios is precisely what you want to get the student to be used to. So I think that the concept... Now, incidentally, my old teacher, Brescia, I took general chemistry. Brescia was one of my laboratory instructors at City College. I was glad to see Brescia did say that now in the middle of toward the end of the 20th century, it's time to get rid of the concept of normal solutions. So I think part of it is in teaching of general chemistry is to try to use those concepts or those new discoveries which make the concepts easier to understand and get rid of the ones that are pretty well obsolete. And these days, most good undergraduate schools use pretty much the same textbooks. In fact, This is the problem in the universities, is that when they talk about teaching and research, it turns out that, this is my general philosophy, the difference in output between a competent teacher and a superlative teacher is not all that great. You may turn out a few students here and there, but in general what happens is the smart ones learn it anyway. The smart ones learn in spite of you, the dumb ones never learn it anyhow, and in the middle you hope you do a little bit of good. But the difference between a competent and a superlative researcher is measured in orders of magnitude. And the reason why, although some people sneer at these top-notch university going after stars, or we may call them hotshots and the like, the reason they go after these stars in terms of research per buck, no matter what they pay them, well, in research, no matter what you pay somebody, the best person is the cheapest one. As a matter of fact, I found the same thing when I was hiring in research. The worst person you can hire is the one that's not quite good enough to keep and not quite bad enough to fire. Because they stay on for years and they take the position of a really productive person. I find out, incidentally, that in the industry they tend to pay lip service to this. They used to say, well, you know, we don't have unions, and therefore we don't pay everybody uniformly. But very frequently, if someone is real good, they would say, well, his salary's due and you get out of line. I don't have much sympathy with that. And I found out in industry that those are the days when they would pay women less. And I think, fortunately, that's gone. I remember I once got into a discussion with my boss. We had a lady chemist, and still, well, you know, she's a woman, doesn't have family responsibilities, we would pay her less money. I said, do you pay somebody more money when they have 6 kids? He said, no. I said, how about paying her for what she does and let her worry about what she does with her money? I guess that was fairly advanced. I guess I was fairly advanced. Incidentally, the company ended up losing me. They deserved to. She's a very good chemist.
How would you compare students when you were an undergraduate to your last year of teaching?
Well, of course, I went to a very selective school, highly competitive school. I think what happens is, in a school that's not very competitive, the smart students are just as smart as anybody, but they get very many that just have difficulties. But I think what happens is, the students that are really slow generally find some major other than chemistry. So if you're talking about chemistry at the introductory level, then of course you get some that are smart and many that aren't. And as the courses become more advanced and more selective, then you find better students. But I would simply say that some state universities, because they're less selective, their smart students are as smart as anybody, and their poor students just drop out.
Well, probably the majority of people finishing freshman chemistry have less than a pleasant memory of it. What could be done to have most people leave freshman chemistry?
Well, we used to put out student evaluations. We used to have students evaluating what they got out of the course. And as I used to say when I would hand out my student evaluations, I'd want to know, ask the students for 3 things. I'd want to know, is there any extra work I could do to get a better rating? Could we postpone it for a week? And do they grade on a curve? But from the evaluations we got, we found out that most of the students that took our advice and didn't get behind did reasonably well. So I would say that not everybody has a bad taste in their mouth from freshman chemistry. Some enjoy it. Some enjoy it and do very well. And I used to tell them that they already had an excellent set of notes. It was known as a textbook. And if they would bother to read it before the lecture, they would find they have to take much fewer notes and they'd get a lot more out of lectures. Incidentally, in my later years, I taught a course of freshman honors, which were very bright students and very demanding, and a very challenging course. One of the teachers now is at Kent State is Professor Gould, who has written some standard work on mechanism of organic and inorganic chemistry, and he doesn't lecture at all. He simply makes assignments and puts students on the board and has them do problems. And he got a lot of gripes on that, but it turns out that it's a very effective method. And near the end, I was doing that when doing less lecturing. One of the few things I learned in my history of education courses where lectures came from. Lectures started in medieval days because only the professor had a book. And one therefore has to consider to what extent one should simply repeat what's in the book, or whether one should force the students to read the book and learn from the printed page. And I think that if classes are reasonably small enough that you can put people on the board and assign problems and have them do problems that you force them to do it, you force them to be active. And I'm rather impressed with Gould's technique, and I used it more and more. I did an awful lot of board work in the end, but when I had a small enough class. And they recognized that every time they came there, they were going to be up on the board, and they would have to do their stuff, and they would read the book. And but most of the time, the ones that gripe about chemistry are the ones that find all kinds of good reasons not to do it. Because really, with the texts, with most of the texts as they are now, I think a reasonably mature, I wouldn't say mature, but a reasonably diligent student really can learn right out of the book.
Well, what's been your most frustrating thing in chemistry?
Finding enough time to do what you want to do.
How would you say you divided your time between research and teaching at Kent?
Well, teaching loads were higher than they should. Teaching loads are somewhat higher than they should have been. And I think if they were lower, I would have gotten more. I probably would have gotten more granted. But also, I would say we didn't have that many graduate students. I think I was rather fortunate in the graduate students I did get. I would say again, the teaching. I like teaching, but the idea of saying there's no conflict between teaching and research. There are so many hours in a week, and if you do more of one, you do less of the other. And the question is, how should it be balanced? And I think my own philosophy in a teacher is that you start everybody out on a fairly low teaching load, and then you see what he produces. If they don't, if you tenure somebody, and then they turn out not to do very much research, then they should be teaching. I've seen some time where there would be criticism when a school refuses to give tenure to a very gifted teacher who hasn't done any research, and it depends. If he was a gifted teacher and he only taught half-time, then he hasn't turned up with anything for the other half of his time. But my feeling is, one way or other, you have to earn your keep. And if you many of the researchers will want to do it through some teaching, but again, this is the kind of a balance that you can have. And one way or another, you have to fill up the week. What had happened is, I think that, Kent State, I think, was an organization that metamorphosed from a teaching college, and I think their development got stuck in the middle. So where part of their teaching was part of their, some of the departments were PhD granting departments and others were not. And I think that the university administration tended to feel the pressure to have higher teaching loads. That's life.
Well, have you tried to trace your ancestry back to where your parents came from, or have you just sort of cut the cord and? Well,
I had a distant relative that tried to track them down. Unfortunately, most of the records now, I can go back as far as I knew my grandfather, but most of the records are destroyed.
But you've never felt you were...
There was, no, I had a distant relative that I picked up in Israel. I think almost everybody in my father's hometown was wiped out. There were about 12, there were about a dozen people that come here. But I haven't had contact. In a way, it's too bad, but I was never. I don't think I could trace them back. It's unfortunate. It's not as far as it goes. I think that on my wife's side, they can trace it back somewhat further. But you know, Pens, the further back you go in your ancestry, the more diluted it gets. It's so. You know, you may there's the the idea that everybody is descended from King William the Conqueror in England, and of course everybody is, because if you raise 2 to the power of the number of generations, it's interesting because well, in the New Testament, for example, I believe they trace the descent of Jesus to the house of David. But when you consider the number of generations that they trace, everybody would have been descended from the house of David. The answer is I would like to. I know some stories about my great-grandfather, but further than that, if we were to go back and look at the records we probably would find the villages have been leveled. So I guess I'm just here.
Is there any topic we've overlooked that you could?
Oh, let me think. You've done a pretty good job, actually.
Well, we haven't covered your wife. Was she housewife, or did she work also?
No, I guess I messed up her career. She was going to go to the social work school and was accepted Smith and got married too. And then we had a couple of kids she was thinking about. She didn't manage to get herself a master's degree in letters at Pitt because they wouldn't give a master's in social work at that time. And then she had a couple. She's an only daughter, and she really took care of her parents. Right now she's doing volunteer work of all kinds, and taking courses. She's more or less an art buff. She's enjoying herself.
You couldn't talk her into taking piano lessons?
She's not that interested. She does what she likes. I don't know whether she would have been successful as a social worker or not. The reason I say that is that she's excessively logical. Now you see, many times I remember one time she has a cousin who comes from a very wealthy family, and I once saw the cousin's report on a woman that was having trouble making ends meet, and she had all kinds of good reasons why. But when I saw what the woman was getting was I don't know whether she would have been successful as a social worker or not. The reason I say that is that she's excessively logical. Now you see, many times I remember one time she has a cousin who comes from a very wealthy family, and I once saw the cousin's report on a woman that was having trouble making ends meet, and she had all kinds of good reasons why. But when I saw what the woman was getting, it was obvious why the woman wasn't making ends meet. She wasn't getting enough money. Now what happens is, I suppose if you're a social worker or a caseworker and somebody says, what's the matter with these people? And the answer is nothing, except you're not giving them enough. You don't last very long in the job. Or it's very frustrating. So what happens is you either get frustrated or you learn how to give these people a talking to. Okay? My wife tends to be the very logical type. Well, recently, when she was at Duke, she thought she would go get a master's in social work. But everything had gotten extremely mathematical and theoretical. For example, in their sociology department, they may spend the whole term or a better part of a term learning about the scientific method. None of my colleagues have ever studied the scientific method. Okay, so in chemistry, you just do it. So you see but there's been a certain tendency to, I think, sometimes to make up for lack of content by giving everything very high-sounding names. for example, the library of science now, library of science, which in itself is a sort of a misnomer. Librarians are perfectly useful people, but they make library of science a graduate study, so you can't take history of library of science until you have a degree. You can take quantum mechanics and advanced physical chemistry and advanced calculus as an undergraduate, but you can't take a course in the history of library of science. Now, there's something to it. I do think that at the high school level, I would like to see many of the education course requirements reduced sharply. And I kind of suspect that it's first of all important to know what you're talking about. And in terms of teaching, I think that there's not too much you can be taught. I think if you can do it, you don't have to be taught. And if you can't do it, it doesn't do you that much good. It's interesting, there have been complaints, for example, that many college teachers have not had any training in teaching. It's interesting that some of the best ones, some of the ones that haven't had any training are the best ones. It's a common sense approach. But, you know, I guess one finds this out everywhere. You know, if you're a physician, for example, you mustn't allow the patient to get out of your office without treating him because he may get well by himself. I think many subjects have become over-academized, for example. I think nursing training is one. They want to give a bachelor's in nursing so that they can get more money. And I think perhaps the introductory course is designed so that they pick out the smarter students. But really, from the point of view of content, I think that there's much less hands-on work. And as a result, what students do is they now get degrees and don't know anything, and they can go out and get their training. I guess in the old days it was probably the other way around. They would simply exploit them, because once you've made 50 beds, there's really nothing else they have to teach you about. Or they use it for cheap labor. But I would say that right now chemistry is a more mature science. I think that we're competing. Chemistry competes with medicine for the best graduate students who go to medical school because they can make more money. There's probably more action. There's a lot more action. There's a lot of action in biology and biochemistry. And I think we just have to take a competition. I mean, chemistry is going to be in there fighting, but I think we have to recognize that it's simply not moving as fast as some others, simply because you're paying the price of success. But nevertheless, if you look at the journals, you see all kinds of interesting and fascinating new techniques. So although chemistry doesn't necessarily move as fast as, say, plate tectonics, it still moves at a very satisfying clip. But, you know, it's all science. And I guess none of us has been created by God to be a chemist rather than a physicist, a mathematician, or a geologist. It's all science and it's all fun. You have to like it. But I would say that the place I really got turned on into science was high school, by two young high school physics instructors. I recall, though, being somewhat skeptical about this. For example, I do recall an incident with Walter Zinn. It was standard in it was rather standard in the textbooks at the time to use a water aspirator as an example of Bernoulli's theorem. The answer there is you accelerate a flow, and that reduces the pressure. Except there's nothing in Bernoulli's theorem that pressure has to go down to a vacuum. Okay? So it turns out that if you think about it, Bernoulli's theorem does not explain why you get a vacuum. And I refuse to believe that Bernoulli's theorem was the answer to a water aspirator. Turns out it's just entrainment. And it turns out that Zinn, for example, had a professor who written an article in a philosophical magazine. He was able to show me. I think what students have to learn is not to believe everything they see in writing, that they have to work things out. That they should really get in the habit of going through most of the derivations to where they understand them, because if they get in the habit of doing derivations of things that are known, they're developing a facility for doing derivations of things that are not known. And in a way, sometimes in research, you can't always tell. The people that do the best in courses do better in research, but not frequently not the best in research, partly because research is luck, and partly because when you solve problems in your schoolwork, all the problems have answers and you know it. And in research, the problems don't have answers all the time. And of course, you know how to answer questions. And I think that in research, one has to develop a critical facility. Most of the ideas you have are no good. And the trick is to get rid of those as soon as possible so you don't waste your time. My own philosophy when I was at Burt Davis was to have enough ideas, have more ideas around when you have time to work on, so that if one of them turns out to be no good, you can get rid of it and go work on something else. I remember working on one project with Mackay, and it was a catalytic process, and we've gotten ourselves some qualitative results, but after a year, I've never been able to get the yield up, and I was running out of ideas. I remember he asked me how much money we should budget for this project. I said, the project's getting to be a dog. Why don't we get off and do something else? He said, you know, you're the first supervisor that ever suggested we get rid of one of his own projects. And I think that there are times that knowing when to get rid of a lousy project is an important facility to develop. That's one of the things that. But I think different people have their own styles, and they all work. Nobody's ever put it into a little bottle. I just imagine that almost everybody you talk to that's been successful in research has his own style. And I think the term, there are the Apollonians, after Apollo. And these Apollonians are the people that tend to work very logically. They're also intuitively, but they tend to work very logically, very systematically. Their papers appear in logical order. And then there are what's called the Dionysians. And St. George used to say that he couldn't write a proposal because he didn't always know what research he was going to do when he got into the laboratory. Well, that's a little extreme, right? One should know what one's doing. But there is this balance between the people that tend to be very logical, and there's some very fine people in that group, and then there are the group that tend to be rather intuitive, and there's some very fine researchers there. The question not is how they do it, but what kind of results they come up with. It's something that I think we need to understand. Because you can find people, good people, with entirely different ways of doing things, that they seem to come up with ideas. But I do remember one time seeing about someone had, this was a letter of recommendation, and this was someone who wanted an administrative post. The letter of recommendation said how this person had generated more ideas than anybody, and so forth. But someone didn't know how to read a letter of recommendation. What was absent in that letter of recommendation was the person had very carefully avoided saying that any of the ideas was any good. Does that about do it?
Okay.
All right.